So Tessa Fisher is an astrobiologist at Arizona State University in the School of Earth and Space Exploration. So we work together, that's great. Her research is primarily focused on using network theory to develop better atmospheric biosignature and technosignature concepts for exoplanets. And when she's not doing science, her hobbies include dance, singing in her city's LGBT women's chorus, co-hosting the science podcast, A Science Scientist at Bachelor's, and writing science fiction and fantasy. Tessa, the floor is yours.
Thank you. So yeah, today I will be talking a little bit about a lot of what's gone into my dissertation research over the past few years, and essentially it's a different approach to sort of hopefully better understanding the chemical patterns of behavior in exoplanet atmospheres. So without further ado, I'll go ahead and get started. So what motivated a lot of this research back when I first started was the fact that in practice, it's actually pretty difficult to go with confidence from being able to say, oh, we have a spectra with such and such features, to saying conclusively that there is life on an exoplanet. Um, and so I guess the goal for this was to develop a more robust um, way of assessing the possibility that what we're seeing spectrally is a biosignature. And, there are a lot of potential pitfalls with assessing biosignatures for exoplanets. Big one is the risk of false positives. We used to think that, oh, if we just find oxygen in a planetary atmosphere, that means there's life there. Except now we know that there are ways you can get, in some cases, potentially quite a bit of oxygen that have absolutely nothing at all to do with life. So obviously that's a problem. Another issue is the fact that a lot of our biosignature detection is geared towards life that is similar to our own, breathes oxygen, uses water as a solvent, is carbon-based, etc. And depending on how different the biochemistry is, we, of a given biosphere, we may not know what molecules in an atmosphere are biologically relevant. So basically, we were hoping to come up with something that is more reliable in the face of potential false positives, and hopefully that's more universal, that will work no matter how radically different the biochemistry involved might be. Um, and so the approach we decided on was inspired by the fact that we pretty much never find, at least here on Earth, life in isolation. You never just find one life form and then nothing else. It's usually found within a pattern of interactions between a whole host of different life forms and their environment. And something that's really good for analyzing patterns of interactions within complex systems, such as an ecosystem, is networks. Now, when I talk about measuring networks, what do I mean? Well, there are some very simple tools or metrics that you can use for sort of analyzing the shape and characteristics of a network. And again, network is literally representing any complex system by assigning each of its subcomponents a point on a graph and then connecting them to each other based off of how they interact with each other. A classic example of a network measurement is degree, which is, in plain English, the number of connections to a given point or node in the parlance of a network. And the mean degree, as the name suggests, is just finding the average of that for the entire network. So that can give you an idea of, on average, how interconnected are each of the points in your network, which can be useful, as you might imagine. Another network measurement I'll talk a lot about is shortest path length, which, as the name suggests, is the shortest distance between any 2 points or nodes in a network. And as is the case for degree, you can also find the average of this, which, again, the average shortest distance across the entire network between any 2 given points. So these are, just fairly basic metrics, but they can be really useful. The other cool thing you can do with networks is that you can incorporate more information into them by weighting them. That is, for example, you can integrate information you have about the connections between the components into the sort of links or edges between them. For example, in this really simple network, let's say that the edges are weighted to represent physical distance. Now, in an unweighted network, if you want to know the shortest distance between points A and point C, really simple. You go from A to B to C. However, in this weighted network, the shortest distance between A and C is actually going from A to B to D to C, because that has a weighted distance of 5, whereas the weighted distance between A, B, and C is 6. So essentially, this is a really powerful addition to representing complex systems as networks. You can get a lot of information into a network representation by weighting it in such a manner. And these weights can represent anything, just any information you have about the interactions between the two, the components of the network. Now, you may be wondering, how do we apply this to atmospheres? Well, you can create network representations of chemical systems too. It's pretty simple, actually. You basically just take all the different species present in your chemical system, as you see here in this sort of toy network, and represent them as points, and then connect them based off of what reactions they go participate in. So it's actually fairly straightforward. And kind of the reason we decided to do networks in the first place was inspired by this paper by these two network scientists back in 2004, Soleil and Montagneux, who went through and did this sort of network analysis for every major planetary atmosphere in our solar system. And what they found was that while most of the atmospheric chemical reaction networks in our solar system looked like this, I believe this one is from Mars specifically, basically this sort of tangled mess of spaghetti that looks chaotic and random, the chemical reaction network for Earth's atmosphere looked like this, which is a pretty striking difference. It also had some unique characteristics. It was modular in that you could divide it up into smaller self-similar component subnetworks, and it was also hierarchical in that these subnetworks fed into larger subnetworks that fed into larger networks in turn. So very unusual characteristics that they didn't see in the other planetary atmospheres. And inspired by this, we wanted to see how this really stacked up, since Soleil and Montagneux, like I said, were network scientists. They weren't, atmospheric chemists or planetary scientists or astronomers. They mostly just did this to see what would happen. So we wanted to try to take a similar approach, but in a much more rigorous fashion. So before we decided to try to apply this to terrestrial planets, we needed a proof of concept. How do we confirm that what Soleil and Montagneux saw wasn't a fluke, and that the network metrics, the network properties of an atmospheric chemical reaction network can actually tell us something about the physical and chemical state of an atmosphere? And the way we decided to test this was with hot Jupiters. Did this for a couple reasons. First off, despite the fact that, so far as we know, they are completely uninhabitable, hot Jupiters are one of the few types of exoplanets that we actually have decent-ish atmospheric spectral data from. So, this is like actual physical reality that we're looking at. They're fairly simple in terms of what drives their behavior. Chemically speaking, it's mostly the temperature, the depth of the atmosphere, and the initial composition. So, there are only a few initial parameters that, you have to worry about. And the other thing is that, and this is just a cool fact, there's actually a wealth of kinetic data for the chemistry in hot Jupiters, because it turns out the conditions on a lot of them in terms of heat and pressure and composition are actually pretty similar to what you see inside an internal combustion engine. So there's a whole lot of data from the car industry that makes life a lot easier having that kinetic data. So that's kind of why we started with hot Jupiters. So to sort of test this proof of concept. Oh, well, rather, before I get into that, I should explain that in particular, we wanted to see how well network metrics correlated with atmospheric thermochemical disequilibrium. Mostly because, in the tradition of astrobiology, the thought is often that, an atmosphere that is out of chemical equilibrium is where something interesting is happening. Life is very good as a process of driving systems out of local thermochemical equilibrium. So that's why we started looking at equilibrium disequilibrium first. Now, for hot Jupiters, how we decided to quantify the distance from equilibrium was using vertical mixing coefficient, or KZZ. So the idea here is basically that at a KZZ of 0, there's no mixing between your layers. Your planet's atmosphere is perfectly stratified, and each layer has basically come to thermochemical equilibrium. At KZZ above 0, you're having mixing between the layers, and as a result, that can drive your planet away from thermochemical equilibrium because, for example, you are getting certain species dredged up from sort of the deep, hot, high-pressure interior where certain reactions may be more favored, and having that sort of flux moved upwards into cooler, lower pressure layers, and introducing species that at higher abundances that would normally form at equilibrium. So, anyways, basically, the take home of this is that the higher your KZZ value is, the further you are away from equilibrium, is how we thought about it. So, to do this, we basically established a pipeline. We would model a sort of whole variety of hot Jupiter atmospheres at varying pressures and temperatures and initial compositions using Vulkan, which is an open source modeling package. We'd extract the reaction list from the converged models. We would build a weighted network, by assigning each species in the reaction list a point, connecting them based off of what reactions they participated in, and then weighting those connections or edges based off of the flux, so sort of the amount of material moving through each reaction. Having built the reaction, we would then measure the topology and then compare the distributions of the resulting topology metrics to see if we could distinguish between them based off of how far the initial models were away from disequilibrium, or from equilibrium, rather. And when we talk about comparing distributions, there are a couple ways to do this. The one we used the most was the Kolmogorov-Smirnov metric, or KS metric, which is basically just a measurement of how statistically distinguishable two distributions of data are from each other. And these are just some simple distributions. As an example, the one on the left, they're basically almost identical. And so you have a very low KS value. And also the KS metric produces a p-value, which tells you how significant it is. So in this case, the p-value is very high, which tells you that whatever statistical distinguishability between these two metrics is not very statistically distinguishable. On the right, you have two very different distributions, and as a result, you have a high KS value. The closer you are to one, the more distinguishable your distributions are from each other statistically, and a very low p-value of 0, which tells you high statistical significance. So the other thing I'll talk a lot about when I'm talking about the hot Jupiters is sort of the initial distributions or the distributions of initial conditions. We mostly sorted out based off of temperature. So if I talk about a distribution at 1200 K, what that means is that there is a Gaussian distribution of initial conditions, in this case temperature, centered around 1200 Kelvin. By the same token, a 2000 Kelvin distribution refers to a Gaussian distribution of initial temperatures centered around a mean of 2000 Kelvin. So that's what that refers to. And so these are kind of the initial results we got back of the different distributions. as a function of, or the um, sort of probability. These are all kernel density estimator distributions. So this is essentially a probability distribution of the distribution of different network metrics from the resulting networks. The green is all the networks that were drawn from atmospheres at KZZ of 0. The magenta is at atmospheres of KZZ equals 10 to the 10. So, at equilibrium and then very far away from equilibrium. And these, I should note that these network measurements are all in log form. And you can see here that with some of the network metrics, you can't really distinguish between the equilibrium distributions and the non-equilibrium distributions. But some of them, such as the two on the bottom, which are node between centrality and average nearest neighbor node degree, are really useful for or show a high distinguishability between the two distributions. And we also, because we figured there's going to be a fair amount of uncertainty in sort of observational data, we wanted to see if this was true even when you had a lot of uncertainty in, for example, what the actual temperature was. And it turns out, even up to 250 Kelvin uncertainty of plus or minus in terms of temperature, these network measures, node betweenness, centrality, and average neighbor degree, are still pretty good at distinguishing between equilibrium and non-equilibrium atmospheres. So this was really encouraging to see that, this actually works and will actually change as the physical and chemical state of the atmosphere changes. The other thing we wanted to do to sort of confirm that we were seeing, that the network measurements were actually reflecting changes in the physical and chemical state of the atmospheres. We did some perturbation testing. In this case, we knocked out the pathway of CH4 being converted to CO, which is pretty important in determining sort of the chemical behavior of hot Jupiters, and then compared the resulting network metric distributions to see if you could distinguish whether or not you're looking at one of the perturbed models or not. And it turns out you can, both at disequilibrium and at high disequilibrium and in the equilibrium cases. In some cases, very dramatically, looking at nearest neighbor node at the very bottom, or average neighbor degree rather, at the very bottom, you end up with very different distributions. So that was also very encouraging to hear and helped confirm that these network measurements are actually reflecting changes in what's actually physically going on in the atmosphere. The other thing we did, and this was one of my lab mates' project more than my own, but I'll talk a little bit about it, was wanted to see if we used these network measurements as sort of the input for predictability algorithms, using a machine learning technique, how effective or were they in helping boost the accuracy of the predictions? So basically, if you were to feed in the network topology data that we've sort of analyzed into a predictiveness score algorithm, how accurate would the resulting machine learning algorithm be in predicting the equilibrium or the level of disequilibrium of the atmospheres that generated those networks? And it turns out in a lot of cases it's pretty good. In some cases, even better than just looking at atmospheric composition alone. And that this is true over a wide range of temperatures. So this was also really good to see, and suggests that we have a useful tool here potentially. If you want to read more about this, we had a article in the Astronomical Journal last year, which will go into much more detail about how we did this and what our results were. But that is what I've just given you is basically the highlight of it, of sort of hot Jupiters and sort of how we set up this proof of concept before we moved into looking at terrestrial atmospheres and potential biosignatures. Which brings me to the next part. The part that I was particularly excited about as an astrobiologist was, does this work with terrestrial worlds, and can we use it to potentially detect the presence of biospheres? And so to do this, we basically modeled planets with and without life and ran it through the same sort of pipeline, compared the resulting distributions of network topology, and then went and saw if we could use these differences in the distributions as a potential biosignature. So to start off, we figured we'd do something simple, relatively speaking. So we did Archean Earth, modeled about 20,000 Archean Earth atmospheres using the Atmos modeling package. These were divided up into 4 sets of atmospheres. The first set basically just has a abiotic surface flux of methane primarily from serpentization, since that is something that people who are looking at terrestrial planet biosignatures have been worried about as a potential false positive. The second case is we actually do have a biosphere pumping out methane, and that is explicitly included in, or rather the methanogenesis reactions, the biological methanogenesis reactions are explicitly included in the chemical reaction network. The third case, we just have a high methane surface flux, about the same level as the methane flux you get from the methanogenic biosphere, but we didn't make any assumptions about what was producing it. So, a methanogenesis reaction was not included. We're just assuming that for some reason this planet is putting off a lot of methane, and we don't know why. So that's another potential false positive case. And then lastly, we just had an atmosphere that, for whatever reason, naturally has high levels of methane on the same level, on the sort of same magnitude of the planets with methanogenic biospheres. And it's not a surface flux, it's just kind of there. Maybe it's left over from its primordial formation or something. So basically, we have like the one biological atmosphere here, and then 3 potential false positives. And we wanted to see how well we could distinguish between all of them. And the results we got for this were also pretty encouraging. So this is the, again, kernel density estimator plots for the different network measurements, plotted against the abundance of CH4, specifically as mixing ratio, in the planet's atmosphere. And in the case of looking at the abiotic flux planet, where you have serpentization, versus the one with biotic flux, they are very different from each other, although it's worth arguing as well that the biotic flux planets end up with a lot more methane in general. So, that alone would probably be a pretty big clue. But still, it was encouraging to see that the network measurements were also very distinct from each other. If you look at the case of the biotic flux versus this abiotic steady state, where again, your planet just has a lot of methane in its atmosphere for some reason, even though the methane flux, or the methane abundance, I should say rather, ended up about being the same, the network measurements, the distributions are very different from each other in a lot of cases. So that was encouraging to see. And particularly looking at stuff like clustering coefficient and node between centrality. If you're looking at the biotic flux versus the anomalous high flux, where again, your planet has a really high methane flux, and we're not making any assumptions about why, it's a little more difficult to distinguish between them, but again, we are still getting some separation between the network measurement distributions for the biotic flux versus the anomalous high flux. Or at the very least, we're putting more constraints on what distributions are going to be associated with a biosphere. So again, this is very encouraging to see. We also did some perturbation testing. Um, Again, same reason before, we wanted to confirm that what we're seeing actually tells us something about the planetary atmosphere that's actually going on. In this particular case, I knocked out any pathways that were involving settling, so C2H2, which is really important in haze formation. So knocking that out will really change the characteristics of your atmosphere. Um, and in the case of the biotic flux, you ended up with very clear separations in the network measurements. So that was also encouraging to hear, or encouraging to see, good confirmation that, again, we are depicting something that's actually happening in physical reality. And then I also did uh, evaluated how well we could distinguish between these distributions using the KS metric that I mentioned earlier. Um, and yeah, in the case of looking between the biotic flux and the abiotic flux, like I said earlier, just looking at methane abundance alone gives you a pretty high KS metric, which, like I said, isn't too surprising. However, if you look at the other false positive cases, the steady state or the anomalous high flux, in most cases, you perform a lot better in terms of statistical distinguishability between the distributions using network measurements than you do using methane abundance alone. So again, this was something that was very encouraging to see, and kind of confirmed that potentially there's use here as a biosignature. So we also wanted to see if we could do this for industrial emissions in addition to just biological ones. In this particular case, we looked at um, a set of modern Earth atmospheres, and there were about 10,000 we modeled, again, using Atmos, the modeling package. Half of them have CFC12, also known as Freon, which is a fairly notorious chlorofluorocarbon. It's really good at catalyzing the destruction of ozone through the formation of chlorine radicals. It's what the Montreal Protocol in the 80s was all about, was limiting its production to avoid destroying our ozone layer. And in half of these models, we had a concentration ranging from uh, mixing ratio from about 10 to the 6th to 10 to the 8th. And so, a wide range of concentrations. And then we ran it through the same pipeline to see if what the resulting network metric distributions would look like. In this case, it was pretty stark. The network metric distributions for CFC12 really like to cluster around certain values in a way that the models that didn't have this industrial pollution do not. So that's kind of startling. And in particular, something we found interesting is that, especially if you look at the KS values and compare them to the KS values for the terrestrial worlds, you see something like, mean degree is and getting ahead of myself. Average source path length are a lot more distinguishable between each other, between the distributions compared to, say, looking at the examples with the methanogenic atmospheres. The reason we think that is due to how the chemistries work. Essentially, in the case of the methanogens, methane itself, there's obviously having a huge flux of it is going to affect your chemistry, but as an individual species, it's not as reactive compared to CFC12. And so the effects on the network you have of pumping in a lot of CH4 are going to show up more in the network measurements that look at like sort of the whole behavior of the network, like node between a centrality and average neighbor degree. Whereas with CFC12, since it is so reactive, or at least the free chlorine radicals that it produces are, um, just having it as a single species by itself will really affect your mean degree, since that is a measurement of how essentially reactive individual species tend to be. So in some respects, this wasn't too surprising to see that, which network measurements you're using, or which network measurements are going to be more effective is going to depend a lot on sort of what you're looking for in terms of how it influences the atmospheric chemistry. So, having, seen some very positive signs that this is potentially useful for detecting biosignatures and technosignatures, where do we want to go to next? First off, the one thing I would love to do, and actually attempted to do, but we couldn't get the models to work properly during the time that I had to work on them, was looking at sort of the atmospheres that I mentioned way back towards the beginning, where you have, oxygen production that's non-biological, and measuring the network topology of those worlds and then comparing it to atmospheres where the oxygen production is, like on Earth, primarily driven by the biosphere. Something I would also like to do is look at atmospheres like, say, Titan, that have a high degree of chemical complexity. In Titan, you've got all sorts of different radicals in the upper atmosphere mixing with stuff in the lower atmosphere, to see essentially, could this potentially be a false positive? Are we just detecting chemical complexity, or is it specifically due to the presence of biology? And then, of course, the holy grail would be figuring out essentially how do we, practically speaking, generate these networks from spectra? What is sort of the lowest resolution network required to use, or to produce statistically distinguishable results if you're looking for, say, a biosignature? And are there any spectral lines that are associated in particular with specific network motifs or structures? Essentially defining what would we actually need in terms of observations to apply this technique and to build these networks and to use this practically as a biosignature. So, that is kind of what I'm hoping the next phase of the project will be. And on that note, I am hopefully going to be graduating with my dissertation, defending my dissertation sometime in April, May. And if you're looking for a postdoc and you think what I'm doing is cool, let me know, because I need a job. And yeah, any questions?
Thank you very much, Tessa. That was super interesting. So if you have any question, you can either raise your hand using the Zoom button or post them in the chat. While I give people time when I give people a little bit of time to gather their questions, I do have one, which is if you go back to the subplot for the CFC12 scenarios, why do you think there is such an intense clustering here compared to the terrestrial worlds where the distinguishability was more like spatial than
like I said, I think it has to do with the reactivity of CFC12. I think because the chlorine radicals are so reactive, just introducing them radically changes the sort of whole behavior of the atmosphere in a way that methane doesn't. And as a result, you end up in a much more constrained range of potential values because it so sharply defines what's going to be available, because, for example, it's chewing through your ozone. Also, kind of really brought home why it was so important that we, cut down on the use of these molecules, because wow, they really do mess with your planetary chemistry. So I think that's the major reason why they cluster so tightly compared to methane. It's just because those chlorine radicals, man, are just, messing up everything.
Okay, great. Any question from the audience?
Hey, Tessa, that was a great talk. I just wanted to ask, you had at your last slide, you mentioned Titan. I just wanted to see what would be needed to kind of extend this to objects like that.
Time and a decently composed Titan atmospheric model.
Awesome.
Basically all I need.
Well, there's a lot of folks here at Goddard that are looking at that, so maybe that's something
So I
that
have
we could look
heard.
at.
Yes, yes.
Awesome. Well, great talk. Thanks.
Oh, thank you.
So there's a question in the chat from Max asking if you could talk a little bit more about the perturbation testing. And so you described it as stopping the conversion of CH4 to CO2, but what about something like a comet hitting? So can you talk more about the perturbation test?
I have not done something like a comet hitting, and actually that would be really cool to do if, you have a sudden influx of water vapor or, carbon monoxide or whatever. Honestly, the sort of like perturbation testing we did was probably very physically realistic. It's not very likely you're going to have a planet that has really high CH4 abundance that's just going to stop converting it to CO. So it was more of like a, I guess, for lack of a better term, a sanity check than anything else. I would like to do more realistic perturbation testing. So, what happens if you swallow a moon or if you get hit by a comet or whatever, because I think that could be, that's also something you have to worry about in terms of false positives of what if what you're seeing is just a really odd one-off that has absolutely nothing to do with life or what you expect it to. But B, it would also be like something you'd be more likely to actually see.
Great. Any other question? I had another one, which was for the hot Jupiters paper. Why do you think in that case it was node betweenness centrality and mean neighbor degree that were the most relevant network metrics to look at?
We actually know this one. So in that particular case, the way the chemistry worked out is that there were only a handful of species that really influenced the overall behavior of the network, or that really changed, I should say, as we, messed around with temperature and composition, etc. And it was kind of similar to the methanogenic planets in that because there are only a few species changing as you cranked up the temperature or whatever. Network measurements like mean degree, which are really reflective of the behavior of individual species in the atmosphere, weren't very sensitive since most of the species aren't really changing. So it's stuff like node betweenness centrality and average neighbor degree, which are very good at capturing the knock-on effects over the network as a whole that are going to be a lot more sensitive in those cases, if that makes any sense.
Yeah, that makes sense. Thank you. Any last question for our speaker? Okay, well, if that's the case, we can end a little bit early. So thank you very much, Tessa, again, for giving your very interesting talk. And good luck for your graduation.
Oh, thank you.
And yeah, well, thank you very much, everybody, for coming. The next seminar will be next week at the same time, and details will be emailed to you very soon. Have a good day.